So my lecture is about introducing us to lattices. We've talked about them a little in the past, in the last lecture, and a few words here and there. And basically, lattices are discrete subgroups that are, in some senses, large enough that the quotient will be of finite measure. We'll see more examples soon. A few name droppings that are for more advanced lectures are that lattices resemble their ambient group. So, for example, a lattice is amenable if and only if the ambient group is, and it satisfies, for example, Kashtan property T if and only if the ambient group is. And there is a Borel density theorem that tells us that in some groups, algebraic groups, semi-simple, lattices are Zariski dense. But these are for more advanced lectures, and we like to get the basics underway. So, okay, this doesn't work. So first, I'd like to recall some basic things. Throughout the lecture, G is locally compact group, and H or gamma will be closed subgroups, and gamma will usually be discrete. Recall that, and we have a Haar measure mu on G. Left Haar measure. And recall that we have the modular function which measures how much, for example, a left Haar measure is different from the right. And we recall it's as follows. Suppose we have mu, the left Haar measure, then its right shift, for example, mu r of A being defined as mu A shifted by r from the right. This will also give us a left Haar measure. So being essentially unique, there's a constant which we call the modular function of G in R, which is the constant multiple of the previous measure mu. So this modular function is a continuous homomorphism from G to the positive reals with the multiplication. We saw it in Uri's course, and it's also a fun exercise. And this, I will use this modular function throughout. Another thing okay, so I want to define, we will consider the quotient of G mod H when H is a closed subgroup. And I want to define what is an invariant measure on it. So G mod H is usually called homogeneous spaces in the literature sometimes. A Borel measure nu on G mod H. It's not a group, it's a coset space, homogeneous space. It's Hausdorff because H is closed. Is called left invariant when nu of GA, G acts on this by left translations. Nu of GA is nu of A for A inside G mod H. So we'll be interested in invariant measures of G mod H.
G is in G.
Hmm?
G.
G is in G. Only G in G. Invariant measure will be of interest, and there's a theorem which I will not prove, but it's a theorem by Whale. There exists such a nu if and only if the restriction of the modular function of G to H is equal to the modular function of H. And for all on H. So H is also a group, it also has a Haar measure, it also has a modular function for a left Haar measure, and we ask that the restriction is the same.
So you can take this as an exercise, by the way. It's not very easy, but it's certainly doable.
Right. You can define the measure in, well, I think you need second countable.
Well,
but let's think about it later. And in this case, in particular,
but by the way, you will discuss sections at some point.
Yeah, fundamental domains
And such. So maybe you will
sections.
need these two. Maybe you will need sections that will appear later in the lecture.
Yes,
If you're
for
taking
the
sections.
exercise.
For the exercise.
Yeah. In particular, the measure on G mod H relates to the measure of G and H as follows. Nu relates to, let's say, mu of G and mu of H as if you give me a function, a Borel function on G, so the integral of fg dg is the repeated integral G mod H and the integral over H of f of G H dH dg. This is the connection between the measures, and an intuitive way to think of this formula, why is it true, is that this gives you a Haar measure on G. So this, the right hand side gives you a Haar measure on G, acting on functions, and it's essentially unique, so you can pick the constant for the measure on G so it coincides. We'll use it.
What does a Haar measure on G? What does a Haar measure on G? The right hand side. So like what,
Yeah.
given that fixing f. Or
There's a way to identify measures with Ladon functionals. It's not sitting that good in my mind, but you have this operation acting on functions. So if you take, for example, indicator functions, it will give you a measure as you think about it in measure theory, the beginning of measure theory.
So news, we want it to be also unique in some sense?
Oh, I'm sorry. I should have said that there exists such a nu, which is Ladon, and essentially unique. Because, I mean, you can take nu to be 0 everywhere. And it will satisfy, which is not so interesting. So yeah, so nu is Ladon and
Essentially unique means unique up to scale.
Yeah, unique up to scale, sorry. So after we have this, we can think about the particular case where H, let H be a discrete, let H be a discrete subgroup of G, and in this case the Haar measure is given by counting measure, so it's definitely the modular function is identically 1 if and only if the right measures are left measures and vice versa. So when counting measure, with counting measure, it's definitely right and left invariant. That we so the modular function of gamma is identically 1. And in this case, so for G mod gamma, there exists such a nu if and only if the modular function of G restricted to gamma is 1 on gamma. Alright? Okay. So now we are going to define what is a lattice. Gamma in G discrete is called a lattice if and only if G mod gamma has finite invariant measure in the sense of the previous theorem. So Padon, non-trivial. So let's think about, let's say some examples before delving into more general claims. And I probably want to keep the examples here so I can go back to them. So the most basic, or maybe not the most basic, but a basic example of lattices. So first is Zn in Rn, and we definitely know that the quotient is simply the tolls, the n-dimensional tolls. Rn is abelian, so it's unimodular, it has an invariant measure, but you don't need all of that to prove it. And an exercise is to any discrete gamma in Rn is, or the form gamma is the direct sum from I equals 1 to k of z vi. So it's integer multiples of some vectors, and it's a lattice if and only if k is equal to n. Because if k is smaller than n, you can quotient and it would be pretty big.
The VI are independent.
Yeah, it's a direct sum.
Direct
so
sum, okay.
can we turn on the air condition? It's a bit sweaty. It's okay. So it's a fun exercise. You can prove it inductively.
The fact this is a direct sum doesn't mean that VI are independent over the rings, which is the case if you want your group to be discrete.
Turn that one on.
Okay, I haven't thought about it.
I mean, you can embed Z square in R, for example,
Okay.
taking A comma B to A plus square root 2 times B. That's an embedding.
Okay.
But
it will
the
be a
image
direct sum.
will be it will be a direct sum, but the image will not be discrete. In fact, it will be
Okay.
dense.
Okay.
And if you want it to be discrete, you must have it, the VI is independent.
Okay. So let's say VI.
How is it discrete? I mean, how is it dense? If it's only Z?
G square.
Every number could be...
the irrational notation, an irrational notation is dense on the slip. That's an equivalent statement. If you mod out
1Z.
1,
Yeah,
if
okay.
you mod out 1Z,
So you get
something that you can think of as an irrational notation of the slip.
Okay, and another example that we've seen is SLN-Z and SLN-R. So last talked about it last semester, and I showed it's a lattice, and in fact it's a uniform lattice. We'll talk about what it means later.
It's a non-uniform.
Sorry, exactly the opposite of what I said. It's a non-uniform lattice. The viewers in YouTube. Another example. Let's just get another example. Okay, the group of upper triangular matrices with one on the diagonal, and for example integer coefficients in the other three coordinates inside the same, just with real. This is called the three-dimensional Heisenberg group, the continuous and discrete. So I don't know if it's standard notation, but the integer Heisenberg group in the continuous one. So the quotient is actually compact, and so this is a uniform, but we'll talk about it soon. So, okay, I will have more examples, but let's prove something first. So not every group, locally compact group, has a lattice. One necessary condition is that it must be unimodular. Unimodular, it's a difficult word. So let's prove that. So claim.
You already did. You already did. You said that.
Let's do it again. So let's. So
Show us the restriction. Delta of gamma should be 1.
Yeah.
He didn't show that delta on G is 1.
Ah, delta on all G.
It does.
Oh, you meant we showed it today?
I thought so.
Okay, I don't think so.
Oh, okay. I was mistaken. Because I thought. Never mind.
Then G is unimodular.
That surprised me.
Okay. So what do we know? So let's assume G as a lattice gamma. So G mod gamma has an invariant finite measure. So invariant, left invariant. I won't really think about left things today. And let's define K to be the kernel of the modular function of G. Now, G mod gamma, you can map it to G mod K surjectively. Wait, I forgot to mention something. Gamma has to be a subset of K. And this is because we know it has an invariant measure. So by the previous criteria, the modular function of G restricted to gamma has to be equal to 1. So we know that gamma lives in the kernel.
Not using finiteness, just only by invariant measure, not by finite.
Yeah, so far yes.
I didn't understand.
For this inclusion, you just use the fact that gamma is discrete.
Yes,
Not
yes, I'm sorry.
Cofinite volume.
Yes, yes, yes. And now we'll use it because we have the mapping G gamma goes to GK. Since gamma lives in K, this is surjective, and the map is G equivariant. So this map, we can push the measure of G mod gamma to G mod K, and it will remain left invariant, and and finite. Let's say phi phi is G equivariant, meaning that it commutes with the action of G. So we push the measure of G mod gamma. So the thing is that K is normal in G. So the quotient is a group, and the measure we obtain is invariant to translations, and it's radon. So it must be the Haar measure of G mod K. So it's easier for me to say it. So G mod K, we showed it has finite Haar measure up to scale, and it must be, in this case, compact, because so G mod K has finite Haar measure, and thus it is compact. Okay, so let's consider now any questions. So let's consider the map of the modular function of G. So modular function of G is from G to all positives, and we know the kernel is K. So actually, if we mod out by K, we get an injection of G mod K to the positive rings with multiplication. So what it means that delta G of G mod K, let's put a tilde here, we factored, so it lives in the positive bits, and this is a continuous function, maybe I forgot to mention, and the image of a compact is compact. So let's think for a moment what are the compact subsets of the real line. If there is an element different than 1, then you can, if it's bigger than 1, you can take iterative powers and it will escape to infinity. If it's smaller than 1, it will escape to 0. In either case, the only compact subgroups are just the identity. So we know that G mod K injects into the identity, so G has to be equal to K, which means that the kernel is everything. So delta G is equal to 1 identically, which means that G is unimodular. Questions?
Yeah, can you explain again why gamma is in the kernel?
Yes. We said previously by the Weyl criteria that G mod gamma has a finite invariant measure if and only if the modular function of G restricted to gamma is 1 in the case of discrete. So modular function of G restricted to gamma has to be equal to modular function of gamma, which is identically 1 because gamma is unimodular. Okay?
Why is the G injected?
Why is this injected? This? Because we quotient out by the kernel, so it's ISO 1.
Is it clear to everybody that a group with a finite Haar measure is compact?
Actually, no.
So let me sketch an argument for this. Take a group with a finite Haar measure, and we know that we can, the measure is the Radon measure, it's regular, so we can find in G a subset K which has more than half the measure. So for each little g, gk, little g times bk has more half the measure too, so it must intersect with k. So each little g, I can writing down this formula, I can find k1 and k2, little k2, such that g times k1 equals k2. So g equals k1 inverse times k2. So it means that big G is contained in bk inverse times k, which is a compact set. So G is compact. G equals.
So yeah, it's a cool fact. I think it might appear again. I want to mention a couple of more general examples.
Sorry, so just to complete my remark then, so there is a theorem of Weil which we haven't seen. In my course, we've seen that every local compact group has a Haar measure. There is a converse theorem saying that if a topological group has a Haar measure, then it must be locally compact. And what we prove now basically is that this Haar measure is finite if and only if the group is compact.
Yeah.
So you have the picture.
Cool. A couple of more examples. Now, suppose, for example, G is discrete. And we ask what are the lattices in G. So G has a counting measure. Its subgroups also have counting measure. The modular functions are both 1. And the G mod gamma, in that case, will also have discrete counting measure because it's an open image. It's an image by an open map of a discrete topological space. So G mod gamma is discrete. It will have a counting measure. It's left invariant. So G mod gamma has finite volume. If and only if G mod gamma is finite. So gamma is a lattice if and only if gamma has finite index. So general example. The next step is what happens if G is compact. So if we have a discrete subgroup gamma in G, so gamma in G discrete is definitely closed. It's an exercise. It's not difficult, but any discrete subgroup of a locally compact group is closed. And since it's closed in a compact, then gamma is also compact. So it's compact and discrete, so it must be finite. And they are precisely the lattices in compact groups are precisely the finite subgroups. Now suppose that G is a billion. Any subgroup H, now H we don't assume yet that it's a lattice. Any subgroup H will be normal. So and G mod H has the Haar measure. So G mod H has finite invariant measure if and only if G mod H is compact. Compact. And in the case of lattices,
So this follows from the remark I made.
yes, it's exactly what we demonstrated a few minutes ago. And in the case of lattices, gamma is a lattice if and only if the quotient is compact. And this is called, this property that any such H has invariant measure if and only if G mod H is compact, this is called property M. And maybe I should set some definition that about what is called uniform or co-compact subgroup. So definition: H in G subgroup is uniform or co-compact when G mod H is compact. So, having, if the quotient has finite invariant measure, if and only if it's compact for any H, then G is said to have property M. Okay?
It's usually uniform only for lattices.
Usually, yes. But people do say uniform lattice,
Yeah.
which make you think that they might be uniform.
Yeah.
That's true.
Yeah. So so when it's a lattice, we say uniform lattice
Yeah.
or co-compact lattice.
But usually if it's a general subgroup, people say co-compact, and if it's a lattice, people say uniform.
Yeah. Yeah.
We don't need G to be compact for it down to be closed.
No. The exercise is without compactness. It follows in any case.
So the exercise is a discrete implies closed.
In locally compact groups.
That's nothing about groups.
Hmm?
I mean,
No,
sort
but
of-
it's not for general topological spaces. Because you have 1 over n in R.
it's discrete.
It's discrete set,
Oh, but okay.
but it's not closed. So yeah, I also thought.
No, okay, it depends. Oh, fine.
So what did I want to do? I talked about co-compact. Okay, if I mention the definition, then let's just think what are the uniform subgroups here, uniform lattices. So this is uniform. It's just the product of circles. This guy is also uniform.
Sorry, again, why is this, why abelian has property M?
So property M tells us, okay, maybe I should have written it better, but let's say this is property M. Why abelian have property M? So G mod H is always a group because H is normal, and it has
okay, finite measure,
so it has Hall measure, and it's finite if and only if it is
Yeah.
compact. So we can, so in abelian groups, lattices are always uniform. And we can ask more in this direction, and I want to prove some. The next step after abelian is nilpotent. Nilpotent groups have their degree, and it's abelian if and only if the degree is 1. So let's talk about the following claim: nilpotent locally compact groups have property M. And the proof will be simply induction on degree of nilpotence. Induction on degree. So the base is simply the abelian. So we have it under control. And recall that if G has degree R, then G mod its center has degree R minus 1. Am I right? Okay. So if Z defined to be the center of G, then G mod Z has degree, nilpotence degree, less than G. Because we have the central oval series, and when you quotient, the last element would just be the center. So it's sufficient to show that if G mod Z has degree property M, which is the assumption of the induction, then G has property M. So let's take, what do we need to do? We take H in G and assume, wait, is it an if and only if in the property M description, or just one direction?
No, a group could be compact without having. I mean, G mod H could be compact without H having finite invariant measure.
Yes. Okay, so let's see what I'm lacking. I just ran it in my head and I think I'm lacking something in the next proof, and maybe we can fix it. So I'm assuming that G mod H, okay, I think I only showed this direction. That's my issue. That if G mod H has finite invariant measure, then G mod H is compact.
Property M is not the if and only if. I mean,
okay.
Is the left. Yeah, that's
okay.
That's
then I'm good. Good to go. And assume with G mod H to be invariant finite measure. Sometimes it's called cofinite, finite covolume, a lot of words. And let's denote I to be this product and closure. So this is the center times H, we take the closure of the product of the subgroups. This is a group because Z is normal. It's enough to have one of them normal for it to be a group, and it's a subset as a subset of G. It's a subgroup of G. And notice, I forgot the claim, forgot the lemma. Is it okay if I open the bubble? So hold that thought. So just the lemma. And basically what I want to do is, it's sufficient to show that what do we want to do? We want to show that G mod H is compact. So H is co-compact. It's sufficient to show that G mod I is compact and I mod H is compact. Why is it true? Because of the following lemma. G mod A, or let's say H, is compact if and only if there exists a C compact such that CH is G. So let's do it in words. Is the claim clear? The claim itself? C compact and G. So let's run it. Suppose CH is G when C is compact. Then G mod H is simply the image of C under the projection. So a continuous image, so the projection is continuous, continuous image of compact is a compact, so G mod H is compact. This is this direction. Suppose G mod H is compact. Now I write it down. So in words. So suppose G mod H is compact. Take a cover of G by pre-compact open sets. Let's say U alpha. Okay? And this, the projection of pi U alpha, because pi is an open map, will be open cover of G mod H. So G mod H is compact, take a finite subcover, and choose the elements in the finite subcover in the G.
Why is pi open?
Why is pi open? It's an exercise in locally compact groups that if you have topological groups, that if G
No. What is pi?
pi, we know what the pi is. Pi is the projection
Okay. I mean a quotient.
from G to G mod H. So assume that I think for the exercise you need that H is closed.
Yes.
Okay, so H is closed. Show that it's an open map.
Actually, this is the definition of the topology.
Not every
You don't need to assume that H is closed. To be precise, you define the topology on G mod H by declaring pi to be an open map.
Right. Okay. And it coincides with the quotient by H topology. Okay, it's the same. It's the same. Sorry.
Hence,
So okay. So the pre-image of the finite subcover denote denote C with its closure. So we take the pre-images, we take the closure. I don't know. The sentence is strange, but denote C with its closure. I don't know if it's.
Which one?
Yeah, the sentence is a bit weird. It's better than I say it. We took an open cover, took a finite subcover of G mod H. We took the pre-images. It's a finite union of pre-compact sets. I'm sorry that I don't write it. It's a bit.
So C is the union?
Hmm?
C is the union?
Yeah. Okay. C with its closure of the union.
Can you repeat the first phrase again? Like,
The weird what?
weird phrase.
Which pre-image?
Yeah.
Pre-image is the inverse image.
No, I mean the whole phrase.
Okay.
Which sounds
Okay, we took. I should have learned how to write clearly. So we have an open cover. We push it. G mod H is compact. Take a finite subcover. Choose the elements in the finite subcover in G.
Okay.
They are compact, pre-compact. take the closure of the union.
Okay.
The closure of the union is compact, and denoted by C. And C would satisfy this thingy. And it's
So say it's not necessarily a group. Say it's not necessarily a
no,
group.
it's not a group. It's a compact set.
It's a compact set. Okay.
Okay, so if you didn't understand it, it's also a nice, a fun exercise. I'm sorry if I did more
No,
bad
it's
than
okay.
good. So what do we know? Why is it sufficient to show that G mod I is compact and I mod H is compact? Because then we continue in the proof.
We want to leave this example. Okay. You said that we want to keep the example.
Oh,
Okay.
well, it's over now. Okay. So it's sufficient to show that G mod I and I mod H are compact. So if G, so since in that case, in case G mod I mod H is compact, then first we know from the lemma that G has to be equal to AI for A compact. And second, we know that I is equal to BH for B compact. Okay, for this we use that H is normal in I, which I didn't mention. But Z is the center.
No, I mean, now you're proving it. You're just using the assumption so far. I mean,
Yeah, but I mean in the assumption of the lemma, I was a group and H was a normal. No, it wasn't. I'm sorry. It wasn't. Okay, sorry. So then, G is equal to A, B, H. With this guy, I denoted by C. So it's CH, where C is compact because the product of compacts is the Cartesian one is compact. If we push it by the multiplication map, which is continuous, then the image is compact. So AB is compact, so G is CH, where C is compact. So by the lemma, G mod H is compact. So now I owe you two things. I owe you that both of these are compact. Do you want to do a break?
at some point.
So after the play.
Yeah.
Okay. So let's prove them. Okay, let's see. Sorry. Okay, so as before, G mod H surjects equivariantly to G mod I. So I has finite covolume. Similarly to what we've done previously, and since I'm sorry.
You want to use induction.
Yes, I want to use the induction hypothesis. Okay, now I see. So I has finite covolume in G. So I mod Z, which is in G mod Z, has finite covolume as well. So what does it mean? It means that G mod Z modded by, since G mod Z has property M, I mod Z, we mod this out, we get that G mod I is compact by the following equivalence. So I mod Z was a closed subgroup with cofinite volume here. So this quotient is compact by property M. Induction hypothesis. So G mod I is compact. Now we want that that I mod H is compact, and then we're done. So why is I mod H compact? Let's see. I'm sorry. I forgot. Okay, H is normal in I, and H has finite covolume in G. So, and in particular, in I. And in that case, the quotient I mod H, this is a group now, because H is normal. Here is, well, I wanted to use that H is normal in I. This has finite measure, so it must be compact. Okay, I may have done it unclearly. Feel free to ask questions.
I think maybe a remark.
Yeah.
So you've shown that extensions of groups preserve the property M. Saying if I have a group,
Central extensions.
yeah. So proving that's what you proved, and corollaries.
Yeah, it's a
For now.
corollary. Yeah. So, I'm moving on. Feel free to ask
Is it
questions.
clear that H is normal in I? Explain. I is the closure of ZH.
Yeah.
ZH is maybe not a closed group, but look at the group ZH, and I claim that H is normalized both by H and by Z. By H because, well, it's the same group, and by Z because this is the central group. So it is normalized by any element of ZH, it is normal in it, hence it is also, hence the closure of H is normal in the closure of ZH, but H is closed.
Yeah, H is closed, yeah.
So H is normal in I.
Yeah, it's a good argument. So a corollary is that central extensions preserve property M, indeed. And let's remember where we came from. We wanted to talk about lattices, and a corollary that I want to write is that indeed in important groups, lattices.
Why only central extensions?
What else?
We
Possibly.
Extensions.
Okay. Maybe someone can explain it better than I.
Yeah, I mean, so maybe you should think where did you use the fact that Z is central here. It is not correct in general, but extensions possess property M. For example, if it would be, then every solvable group will have property M, but one can find two-step solvable group with a lattice which is non-uniform.
Maybe the
Yeah.
posit H is normal to unity?
So it's something.
No. Sorry. Yes. Yes. Here. The normality of H.
So
In I.
So property M, groups that satisfy it, in particular have their lattices are definitely uniform. So in nilpotent groups, lattices are uniform. One can continue in this direction, but there are a bit of, but it's not complete. The next step after nilpotent is solvable.
I'm just wondering, lattices, if they exist, are uniform. So far, whatever you have said does not assure the
Yes,
existence
yes,
of a
yes,
lattice.
yes.
Every lattice is uniform. I think this is the first statement.
Yeah.
Again, sorry?
Every lattice is uniform. Yeah. If they
Yes.
don't, if they are
Maybe
not,
they don't
if
exist
they are
with-
certainly uniform.
Yeah, that is a good remark. Not always we have it. The next step after nilpotent is solvable. Every nilpotent is solvable. You can ask if solvable have property M, and the answer is no, not in general at least. You would need it to be a solvable Lie group, and or at least originally it was a theorem by Mostow that solvable Lie groups have each of their lattices are uniform.
You do want to make a break at some point.
Yeah, after writing this, we'll
Yeah,
take
so-
a bit of a break. So just wanted to mention solvable Lie groups. Have property M, and in particular, their lattices are uniform, if they exist. And just another small remark is that at least for solvable and nilpotent the groups, the theory of lattices is richer, but they are the topic of more advanced lecture, possibly. So let's take a break.